Hi guys, welcome to the Fried Circuit, the CAJCS Full Steam Ahead podcast hosted by Ved Prasad.
And Saksham Sood.
Here we discuss everything related to science, technology, engineering, art, and math.
Yes, and a bit of background about CJCS Full Steam Ahead. We're a student-run organization in the Cathedral and John Connon School, Mumbai. We do projects, host competitions, create a lot of content basically regarding STEAM, which we, like Ved said, is science, technology, engineering, art, and mathematics. We have a coding competition coming up, CathCon 2021, from 6th to 8th August. You can now register for it at cathcon.cathedralfsa.com. You can also go to cathedralfsa.com to check out all of our other work and see basically what we do. Now, on to the podcast. Okay, and today's topic is our most ambitious yet. Today, we're going to talk about space. You know, it's everything
it's
in
biggest.
space.
You can't get bigger than space.
You can't get bigger than space. It's literally everything that ever exists is space. You know, people don't actually realize this, but people, when we think about space, we think of everything outside the Earth. You know, like you leave the Earth, you go to the moon, think of Mars, etc., etc. But like really, everything is space. We are a part of space. Like the Earth is just one blue rock.
It contains everything. Yep.
Yeah, in the middle of a solar system over here, in the middle of a galaxy somewhere. It's just a small part of space. And I think this reminds me of the Rick and Morty episode where they get a flat tire in space and Morty wants to get out of the car and he says the co-op
I remember this one.
there in space.
That one. Yep.
And Rick is just, Morty, everything is in space. Space
and then,
is everything.
And then Morty gets bitten by a space snake because there are snakes in space.
Who knows? Maybe there are space snakes in space. Who knows?
Yeah.
I mean,
like, for now it's science fiction
haven't gone
in
far
a Rick and
enough.
Morty episode, but like could be.
Could be. Who knows?
Yeah.
Anyway, so starting off with space. How big is space? Let's talk about the size of space. With any guesses, any estimations? How big do you think space is?
See, if I had to go with like a rough estimate, I'd go with 93 billion light years. Is that
very specific?
kind of
That's actually correct. People will think that you might have researched this beforehand.
who would have thought?
how do you get that so spot on, mate? But also, like that is kind of wrong because space is actually constantly expanding. Space is constantly, as we know it, is growing outwards. And because of that, it doesn't really have like a definite size. Currently, however, according to our rough estimate, space is, as Wade said,
93 billion light years. That's the most recent finding that scientists have found, right?
That's the best estimate that we can make so far.
It has been smaller in the past and it will continue to get bigger. So it's not constant at all.
Exactly. So like, I don't know, 10 days from the episode airs and comes on YouTube, we're going to be wrong about the size of space. The universe actually started off 13.8 billion years ago in this event that you might have heard of. It's called the Big Bang, where basically all of matter and antimatter that exists today was created from this one singular point and then started expanding outwards. And since then, we've continuously been expanding, right? And so far, the furthest that we can see in space is 46 billion light years away. And the reason we can't see anything beyond that is because the light that is beyond that, from objects beyond that, aren't actually able to reach us. Or they haven't reached us yet.
Yeah, but just to put this into context, 46 billion light years is roughly half the universe's size.
Yeah.
It's a massive distance. So we just discussed, right? 93 billion, the entire universe. This is roughly half of that, and that is an insane size. Also, Saksham mentioned the Big Bang right now, and when the Big Bang actually happened, it happened so fast that, like, as it happened, like at that second, the universe was expanding by a factor of 10 to the power 26 in its linear dimensions, and volumetrically it was expanding at a factor of 10 to the power 78. So at that point, it was the fastest expansion of the universe, and then after that it gradually slowed down. That's how it originated.
Yeah, exactly. And since then it's constantly been expanding. So like the amount we know consistently gets smaller, becomes a smaller fraction of the entire universe. So like every second that goes by, we know lesser and lesser of the entire universe, which is crazy if you think about it. But let's put a number to this. All right, how fast is the universe really expanding with? Like is there a metric that we judge it by?
I don't know, 1 meter every day. That would be my
No, that's way smaller than the actual number. Universe is actually expanding at the rate of 67 to 74 kilometers per second per megaparsec, right? And this number is referred to as the Hubble constant.
Hubble constant. Oh yeah, I've heard
Right?
about this.
Yeah, and just to put to explain the entire thing, it's 67 to 74 kilometers per second, which, as we know, is simply speed. It's just kilometers that are being added
Yes.
on per second. And the third part of it, the megaparsec part, megaparsec is simply a unit of like distance. One
Yeah.
megaparsec is about 3 million light years. What this
Right.
essentially means is the universe is expanding at the rate of 67 to 74 kilometers per second every 3 million light years. So
Right.
the further from a point you go, the further the universe is expanding at those points. So basically, the universe, like the further out from the Earth that you would go, the faster the universe is going outwards, which means that there's a point where you get further enough from Earth where the expansion speed of the universe is actually greater than the speed of light. And those
Yeah.
parts are going away from us faster than light can
Yeah.
travel back, which means there are certain parts that we
That's-
will never get to know exist in space.
Right, because if you think about it, right, it's not just that they're moving out of the way faster than we can look there. Those parts of space are actually moving outwards and expanding faster than the light from its original position can reach our eyes. That
Yeah.
means by the time we actually get to see where those parts of space were originally placed, they've already moved on to a new position. And since
Yeah,
that
no,
rate of
but in the
expansion
case
is
of
always
these-
greater than the rate of speed of light, we'll never be able to see those places.
Yeah, exactly. In these specific areas, we will never be able to see them. So, if space snakes were to exist beyond
Yeah.
where we can see, we never know. So, there's a chance that we never
There could be
find
so
out if
many
space
parts
snakes
of
exist
science
or not.
fiction that may actually exist, but we'll just never know of, just because
Exactly.
the rate of the expansion is greater than the speed of light.
Yeah,
So
yeah.
we
There's
might just
billions of
never be able
planet
to see
stars
them.
out there that we will never even know exist, just
Yeah.
because of how fast the universe is expanding away from us. And we've been putting some numbers across here. We've been talking about figures and just how big the universe is. But let's actually let's take a safari through the universe almost. Let's talk about what all we can find in space, and just how big and just how small are we in relation to how big the universe is.
Right.
Yeah.
So if we talk about Earth, right? Earth is
Hmm.
actually tiny. It is so small compared to the rest of the universe. Like the best way to describe it would be to give you the actual numbers you can compare to the universe. The universe is 93 billion light years in size, right?
Yeah.
The Earth doesn't even make it 2 light years. It doesn't make it to that unit of measurement. The Earth's radius is 6,371 kilometers.
Kilometers.
That's how
It's just everyday
kilometers.
kilometers.
Yeah, that's how tiny the Earth is compared to everything that's out there in space, compared to the solar system and the galaxy and the other galaxies and just everything. And that's the thing, right? We're just one planet, and we just around us we have these bigger structures, like I just mentioned,
Yeah.
the solar system, the galaxy, and there's so many of these individual structures, and all of that combined, right? The millions, billions, trillions of them. That's what eventually makes up space or the universe as we know it. And we're
Yeah.
just this one tiny particle, this one like
We're
speck
one
of
planet
dust in
revolving
the
around
greater
one
scheme of
star
things.
in one system
Yeah.
in one galaxy, and
Yeah.
there's trillions of these things around the universe. But yeah, okay, fine. So let's move out from Earth now, right? What's immediately next to us? The moon. The moon is
Right.
384
Moon's the-
kilometers away from you. So it's basically like a long road trip away from you. It's
Yeah.
7 kilometers, just a couple of 100 kilometers. We've done it before. We've all gone on road trips.
Yeah.
So if you could fly a car in space, you could essentially make it to the moon. But let's go beyond that, Faith. Let's go beyond that. What comes next?
Yeah. Next, we actually have the closest planet, and probably the most
Yeah.
popular one, the one that's being discussed the most today in terms of future plans for humans, and that is Mars. Now,
Mars.
I've said closest planet, so you might expect it to be somewhere in the moon range, right? Like 384 kilometers. That's not true. It's actually 225 million kilometers away.
That's a big number.
Yeah.
Slightly
like
more than a road trip.
Yeah.
You
Again,
can drive to Mars.
the Earth is 6,000 kilometers in radius, and the Moon's 225 million kilometers away. So
Mars.
yeah, taking them
Yeah.
takes a while. And just to put that into perspective, in terms of like vehicles that we have here on Earth, if you took a Boeing 747 jet, right, and you flew it
Yeah.
straight to Mars on the shortest path, it would take you 32 years to reach there. Now, obviously, you can't actually take a Boeing 747 and try to
Yeah,
reach
but
Mars. But just in terms of speed, right? Like how fast a jet is, 32 years to reach Mars.
yeah, you definitely can't drive. But even if you were to take a jet plane, like a jumbo jet plane, it would take you 32 years of your life just to get there. And you know, that might make you think, you know, how do we have rovers on Mars? Or how do we have spaceships on Mars already going there? That's because they don't go at Boeing 747 speeds. So NASA's Curiosity rover, which reached Mars in 253 days, slightly less than a year, traveled at 23,000 miles per hour, which is just try to imagine you going at 23,000 miles per hour.
Right. I think people don't actually understand how fast spacecraft actually are, right? Because what people actually see is the initial launch, right? Just as it's going up from Earth and the first stage is being deposited and all of that. And when that happens, that is very clearly the slowest part of the flight, right? It's just taking off. Right? People see that, and people sort of associate that with the general speed of spacecraft, but that's not true, right? They move they cover thousands and thousands of kilometers every hour, thousands of miles every hour, but people just never get to see that. So most people don't really visualize spacecraft like that.
Exactly. I mean, there's no resistance in space; it's just a vacuum, right? So once you accelerate an object, it doesn't really stop unless you make it stop. So because of that, you can reach insane speeds in space. That's something we're going to cover later on in the podcast as well. You know, just how fast can you go in space. But yeah, okay, fine. We got Mars, right? Let's zoom on a little bit more. What comes next, Ved?
What comes next? Well, the structure that contains everything, contains everything we've discussed: the Earth, the Moon, Mars. We have the solar system, which comprises. I mean, Pluto is not a planet anymore, so
yeah, Pluto got demoted.
8 planets and the Sun, and all the respective moons and asteroids and all of those.
Yeah, the solar system as we know it. Yeah. Just how big is solar system, Ved? I'll give you a drum roll.
287.46 billion kilometers. Now you can see how things are getting
exponentially
larger. Billion with a B. But you can see how things are getting exponentially larger as we talk about them, right? Like first you have the Earth. The Earth is approximately 6,000 kilometers in radius. Then you have the Moon, around 300 kilometers away from the Earth. Okay? Then you have Mars, 225 million kilometers away. And then the entire solar system containing all the planets, not just Earth and the Moon and its nearest planet, 287.46 billion kilometers. Things are getting so much bigger, so much faster. Right. And that's just in the solar system. Like what happens when you reach the galaxy or the other galaxy, the whole universe. That's how eventually you get to 93 billion light years.
Yeah, it's actually insane. But yes, now we move on to beyond the solar system, right? Because as we zoom out even further, we see the Milky Way, our galaxy. And it's here that I want to make a clarification about the units we're going to be using, because kilometers is too small now. Kilometers is just not worth our time anymore.
Yeah, it's now fine for about distances on Earth, but we're not talking about Earth here. We're talking about space.
Yeah, space is a different ballgame altogether. So now we have light years, right? And we've used the term before a couple of times, so I just want to clarify it over here. Light year is not a time unit. Light is unit of distance. It's how much distance light, which travels at the speed of 300 million meters per second, can travel in a year's time. Distance light travels in a year is a light year, right? And the Milky Way, our lovely galaxy, which is our home, is 100,000 light years across. So if you want to go from one point to another point in the Milky Way, that's 100,000 light years.
Right. So which means light, which is the fastest particle we know, right? In terms of motion, nothing moves at the speed of light. Nothing comes even close. Because it moves, again, as Saksham said, 300 million meters every second. Light itself would take 100,000 years to reach the center of the galaxy.
Exactly. So even if you were to travel at the speed of light, which, spoiler alert, you can't, it would take you 100,000 years to cross the Milky Way. Just to put that into context, the entirety of human history is just 300,000 years old. The Earth is 4-point-something billion years old. We've only been around for 300,000 years. So it would take you 1/3 of our entire history, collective human civilization's history, just to cross the Milky Way, if you were to go to the speed of light, which you can't.
Right.
That's how big the Milky Way is. Just our galaxy alone.
Yeah, and there's so many out there, right? Because again, 100,000 light years as compared to 93 billion, right? That just again, it's just putting things into perspective.
We're just getting
and
started
telling
over
us
here.
how, yeah, we're just zooming out a bit by bit and just showing you how small we really are, even in terms of time, right? Not just space, even in terms of time.
Yeah.
Humans have just been around for what, 300,000 years?
Yeah.
The universe has been there for 13.8 billion. With a B. Again, we're
Yeah,
tiny, both
with
in
a
terms
B.
of time and space.
Yeah.
Yeah.
So just
Absolutely
shows how
minuscule.
insignificant like our entire race is in terms of like we said,
Yeah.
time and space. We've barely been around. We don't know anything about the universe. There's some parts we will never see, and there's some parts we can't even travel to, even if we can see them. And there's our Milky Way right now. We're only at our Milky Way now. If we zoom out further, now we're going to zoom out further and see just exactly how far we can go with this.
Yeah.
So yeah,
What's
comes next, Wade? Huh?
No, I was just asking you what comes next. But then basically what comes next
Yeah.
once we zoom out of Milky Way is our local group. Alright? It's a group that contains the Milky Way, but it's not just the Milky Way, obviously. It's a collection of 54 galaxies, right? Again,
Okay.
just to put this into perspective, the Milky
54
Way alone
galaxies.
is 100,000 light years in size. But yeah, it's 54 galaxies, and the entire local group is 10 million light years across. 10 million.
10 million light years. Speed of
Yeah.
light will take you 10 million years to go across it.
Right.
Yeah. we ain't got time for that. If we were to zoom out further from the local group, we come to the Virgo Supercluster, which again, this is all like we're part of it. So the Milky Way is one of the
Yeah.
54 galaxies in the local group.
Local group.
And then The
you get groups of
Virgo Supercluster has
galaxies
many
according to
groups of
Virgo
galaxies,
Supercluster.
out of which
Right.
one of them is the local group, right? So
Yeah.
let's just say, okay, how big is the Virgo Supercluster now? It's 110 million light years across.
Yeah. That's 11 times the size of the local group, which contains 54 galaxies, including our own.
Out of which one of them is the Milky Way, which is 100,000 light
Yeah.
years across.
Right.
Yeah, just puts everything into context, really. Just makes your perspective way bigger. Speed of light
Yeah.
will take you 110 million years to go across the Virgo Supercluster. So all the
Yeah.
Star Trek movies, all the Star Wars movies, all those galaxies, we're not going to be going anytime soon. We're not going to be going to any galaxy anytime soon near us because it's just so far away. Even the speed of
Right.
light will take us so many millions of years to get there.
And we're
But
not
you know
done
what?
with the
We're
group.
not done yet. No.
Yeah.
We're going to zoom out further. What's next,
Yeah.
Wade?
Once you zoom out, you reach the Laniakea
Yeah.
Supercluster, which is
Hmm.
100,000 other galaxies, and in terms of size, 520 million light years. 520 million. We've come to half a billion light years, and the universe is 93.
Just like that. Yeah.
But we've zoomed out. We've gone from the solar system to the Milky Way to the local group, the Virgo Supercluster, the Laniakea Supercluster. We're finally at 520 million light years.
And
Yeah.
we're not done yet. Because
Right.
from the Laniakea Supercluster, we further zoom out to what's called the observable universe. Right?
Right. It's just how much we can
everything in
see.
the universe that we can see. Okay?
Yeah.
It contains 2 trillion galaxies and more stars than there are grains of sand on Earth. Think about all the deserts, all the sand around. Think of the sand that holds your cactus
Every
plant. Think
single
of all
beach,
the playing sand.
everything.
Every
Right,
beach,
every single beach, all the
every
sandy
single
soil, all of
sand pit in a playground, all those
Yeah.
grains added up, it's got more stars than that. And the size of the observable universe, like we've been saying multiple times, is 93 billion light years.
that. Yeah. And that's how far humans have got so far.
That's
But
how far we can
who
see
knows?
so far.
Yeah. So it's how much
Yeah.
we can see, and it's how much the universe has expanded till date, right? It's going to keep going on, and the numbers going to keep increasing. And there's
Yeah.
so much beyond the observable universe. It's just that we can't really see it yet, so we can't measure it yet. Yeah.
True. Yeah.
You know,
According to
we've been
cosmic
talking so
inflation,
much. Yeah.
which is the
Think-
theory that says the universe is expanding.
Yeah.
There is like multiple times more beyond the observable universe that we can't see as compared to the observable universe.
Right.
Yeah, and it just shows,
Yeah, but-
no matter how far
Yeah.
we get, it's just always going to be beyond our reach. It's just a tad bit beyond us. I'm just going to be able to find it. Yeah.
But no, I'm saying we've been talking about light so much here, right? The speed of light and how it's not possible for us to approach the speed of light, or like even come
Yeah.
close to it, right? That and this topic of discussion about the speed of light and how objects and celestial bodies and basically everything in the universe behaves as things approach the speed of light have actually inspired their own branch of physics, right? Or its own topic
Yeah.
in physics called relativity. Okay,
Yep.
because Newton came up with laws for gravitation and laws about mass and matter, and those are fine for normal objects that we have here, right? Like I have
Yeah.
this mouse here; it weighs maybe what, a few hundred grams. For objects this small and that can't really go that fast, even with applied force, Newtonian physics is fine. But when objects are so large and so fast that they approach the speed of gravity, then we need a separate branch of physics, and that's where Einstein came in with
Yep.
his
The
theory
man
of
behind it all.
relativity.
The man, the
Yeah,
myth, the legend,
the greatest
Albert
scientist of all
Einstein.
time, right?
Yep. The greatest scientist of all time. 100%. In fact, he was named the Time Person of the Year for the person of the entire century.
Right.
When the century began, 21 years ago. Entire century, like the entire 1900s, out of
Yeah.
everyone who came and went, all the great rock stars, the bands, the actors, the actresses, the politicians, the world leaders, everyone,
Yeah.
the greatest man, according to Time magazine, was Albert Einstein.
Albert Einstein, right?
And we really can't cover space. We can't cover anything about space or the universe without talking about relativity and Einstein's findings. So basically, Einstein came up with two main theories: special relativity and general relativity, right? And a bit counterintuitive, but special relativity came before, and general came after that, 10 years after that to be precise.
Yeah.
So we're gonna cover those now, and we're gonna talk about how special relativity works. Okay, so let's talk about
Yeah.
special relativity first, right?
Yeah.
There's basically two consequences of special relativity. One's time dilation, and two is length contraction, right? And this deals with
Yeah.
objects that travel at any velocity. Really, relativity works out, but it really starts showing or really starts having big effects when you go close to the speed of light or when you travel really fast, right? And then two things happen:
Yeah.
time dilation and length contraction. So I'm just gonna talk about time dilation for a second over here, right? The way Einstein came up with it was that he was in a train one day and he saw a clock tower, right? And he thought in his head, a thought experiment, that what if the train was traveling at the speed of light, right? So the light coming from the tower showing him the time and him were moving at the same speed. So for him sitting in that train car, the time would never change because the clock would
Right.
remain static and the same light would travel with him at the same time. And because of
Yeah.
that, he would never observe the clock changing. But that's
Right.
only him. The clock would still continue to move. And on like
Yeah.
in that town, wherever he was, people would still see time moving and time would still pass for them. And because
Yeah.
of that, he came up with the idea of time dilation, where basically if an object is traveling really fast, right, or near the speed of light or at the speed of light, theoretically, time would slow down for them. For that person moving at that speed, they would experience time much slower as compared to someone who was observing that person from a inertial or at rest frame of reference. Right?
Right. Yeah, and that, you can really think about it that way because he is inside the train, right? And inside the train, he's moving at the speed of light. So, for him, in that 1 second, he'll already have gone 300 million meters, right? So, but he doesn't perceive time like that. He's perceiving the speed as a regular. He's perceiving the train as a regular train with regular speed.
Yeah.
So, as someone who, if you're inside the train at that point, you believe that
For
the
you, time
speed
has
that the
stopped.
train is, yeah, for you, the speed that the train is going at is the speed that you're accustomed to, the speed at which the world is moving.
Yeah.
So for you, for you, 1 second in outside people's time won't be up until your train has moved 300 million miles. So for him, right,
Yeah.
sitting there watching the clock, the clock just won't move. The second hand over there just won't move at all until theoretically
At
he
the
covers
speed
300
of
million
light, at the
meters.
speed of light, the clock would really never move for him. Because
Yeah, it
as even when the clock moves and that light starts to travel, it would never actually catch him because he's moving at the same speed as the light.
Yeah,
So it would continue to travel towards him as the clock continues to move. The new
yeah, but it would never actually
clock
reach him.
positions
He wouldn't
never actually
he wouldn't
reach him.
actually ever be able to see
So-
the second hand go to the next second.
Yeah,
And that's what
theoretically,
that's what Saksham means. Like time for people outside the train, yeah, the clock tower keeps ticking.
yeah,
Time keeps moving. But for anyone inside the train, time is simply just stopped.
time has stopped. Yeah,
Yeah.
if you were to travel at the speed of light, time would stop for you. Like you could stop time if you could travel at that speed. And I think a very interesting thing about this is is the real... Okay, fine. So actually before that, let's talk about the formula. Okay, because physics, we love formulas. Basically, to calculate how time would change for this person, the person sitting in the train or in the moving object, for him, time would move at the rate of 1 upon gamma into the time of normal people. So if I'm sitting down and 5 seconds pass for me, and Wade's moving in a spaceship at light speed, or at some speed close to the speed of light, for him, the time passed, if 5 seconds passed for me, for Wade, the time passed would be 5 upon gamma. And gamma here is called the Lorentz factor.
Yeah.
Right? Which is, we won't get into exactly how to calculate the Lorentz factor over here. But basically, it's the time passed for the rest of us, or at rest, divided by the Lorentz factor for Wade, who's moving at the speed of light, or close to it. Right? And this was revolutionary. Back in 1905, when this came out, everyone back then believed the speed of light was... that time was constant, essentially. Sorry. The time was constant. And time for everyone moved the same, essentially.
No, his theory wasn't accepted. Like, that would be ideal if it was accepted immediately.
There was a lot of opposition
years later. There was a lot of controversy, and
100%.
Like, it wasn't accepted by the general scientific public. But years and years later, he finally got recognition from other scientists and from publications, government authorities regarding his theories. And that's when people started accepting the theory of relativity.
Exactly, exactly. Yeah. Because everyone thought that time would flow the same for everyone. Like, time for the longest time has been the constant that we use across physics, across multiple quantities, across so many equations. We assume time to be a constant throughout. But here Einstein came up and said, no, time is not actually constant. Time can change depending on who you are, how you're moving, etc., etc. And that fundamentally changed almost everything in physics, because the way we see it, almost all formulae require time unit, which is a constant. But like Einstein said, no, it's not a constant. It really had big waves across physics. And the second thing that we're going to talk about, actually, the second effect of special relativity is length contraction. Right? Basically, it's a smaller, it's not as famous as time dilation, but it's an equally important effect. The way it works is that if Wade was to travel at light speed in front of me, and I was sitting down at rest, and Wade was, let's say, a meter long, right, a meter tall, I would observe him to be at a smaller height than his actual height. For me, his length would contract, right? For like a person who's sitting at rest while he's moving at a very fast speed. Alternatively, for Wade, who's the frame of reference, for him, obviously, he can't grow shorter, right? Like, he's not going to simply become shorter just by moving at a high speed. For him, he's still a meter long, a meter tall. For him, the distance he travels would become shorter. For him, if you traveled a kilometer, if I observed Wade traveling 1 kilometer, he would come back and say, no, I actually traveled 500 meters, let's say, for example, right? It would be a much shorter distance for him according to his whatever unit or whichever tool he uses to measure the distance traveled by him. He would record a much shorter distance than I would for.
I'd record 500 meters, so like that's what I'm using for the example.
Depending on the speed, length contraction would become different.
But also, since we're talking about the speed of light and objects moving at the speed of light, it's also important to talk about what happens when you move at a speed greater than the speed of light, right? Yeah. And that's where Einstein's famous equation comes in. I think this is an equation that's known by everyone, like regardless
the world's
of
most famous equation. I think it is.
Regardless of like whatever subject or stream they're studying, or what they know about physics or math, or what they don't. And the equation, I'm sure everyone knows this, is E equals mc squared, which is energy equals mass into the speed of light squared. And this is actually the equation that you use once an object starts moving faster than the speed of light. This equation comes into play, and what essentially happens here is that it becomes infinitely big, right, in size, and it then requires like infinite energy to be able to push it.
Basically, this equation puts into perspective just how mass and energy essentially are convertible. They're interchangeable, right? So theoretically, that's why the speed of light is the limit in space. You cannot go faster than the speed of light, like Wade said. Why? Because the minute you do that, your mass expands infinitely, which means then you require an infinite amount of energy to be moved. Right? So when you reach speed of light, theoretically, your mass will become infinite, and you would require an infinite amount of energy to move that infinite mass to the speed of light, which is impossible. You can't get that. So because of this one equation, it shows that you can't actually travel at the speed of light, or even faster than that. You always have to be under the speed of light, right? Yeah, and actually, there's an exception over here, obviously, where light travels the speed of light, right? So how does light travel the speed of light? How do we have radiation, gamma rays, X-rays, etc., travel the speed of light? Well, that's because these are in packages called photons, and photons don't
Yeah.
actually have any weight; they have zero mass.
Yeah.
So if you were to apply
they
E
aren't.
is equal to mc square
Yeah. They're simply
on
particles.
them,
They aren't actually like matter bodies with matter or any mass in them. They don't
yeah,
have any
there is
weight,
there
any
is no
matter,
mass.
any mass.
They have zero mass.
They're simply particles. They exist, but they have zero mass.
Yeah, so if you were to multiply 0 into c square, it's 0. So they don't require
Yeah.
energy to move at that speed. That's why light is the only thing that can travel at light speed, or radiation is the only thing
Right.
that can travel at light speed. That's an exception to the rule. Yeah, but also there are, apart from the equation, let's say, okay, fine, you don't want to believe in E is equal to mc square. So what? So what? Just like 4 letters around on a piece of paper. How can they explain whether I can go faster than light or not? Well, there are other reasons as well. One very big thing is that if you go travel at the speed of light, you could theoretically beat cause and effect, which is the fundamental of any science. Like anything in science is based on cause and effect. I hit my hand hurts, right?
Yeah.
A reversal of this would not only break science, it would break everything that we know in like the universe, right? Just this
Right.
logic
Yeah.
purely will just go out the
This
window.
is the basic laws of the universe, right? Like, there's some things that are universal,
Exactly.
like math, for example, right? It doesn't matter where you are in space, what planet you're on, what creature you are. Math still
Yeah.
applies, and math still works because it's one of the fundamental laws that govern the universe.
Yeah.
Like this, we have cause and effect, and you just can't break it. But if theoretically you could move faster than the speed of light, you would be breaking cause and effect, which is the very
yeah.
set and like rigid order in which events happen.
Yeah, that's like there is nothing if cause and effect don't exist. If
Right,
my
yeah.
hand starts hurting and then I hit my hand,
Yeah.
like it can lead to all sorts of chain problems that you can see around the world, right? And if you travel at the speed of light, you could theoretically beat cause and effect. Like you could make something happen and then have the cause of it happen later after that, which is just insane. It's beyond comprehension and it's just not possible as far as we know right now. And because of that, Einstein said and established firmly that the speed of light is the speed limit of the universe. You cannot go faster than the speed of light. You can't even reach the speed of light actually. Because
Yeah.
it will already be cause and effect, which will break everything, and that's why it's not possible. We'll actually come back to this a bit later when we're talking about other stuff. But let's move on, right? So this was special
Yeah.
relativity, 1905, Einstein's great achievement discovery, right?
Right.
10 years later, he actually moved on and created what's called general relativity, right?
Sounds well
Which
known,
is
but it is also
Yeah.
very important.
also very important. In fact, that's what we use today to replace Newton's laws of motion, essentially, or gravitation around the universe, to get very, very, very accurate predictions of when stuff's gonna happen, how stuff moves, etc., etc. With what's general relativity? Take us through the theory. How does it work? What's it talk about?
Okay, so as Saksham said, right, general relativity is kind of a replacement for Newtonian physics, where special relativity is for the special circumstances in which an object is moving at a speed that's close to the speed of light or at the speed of light. But what about the rest of physics, the rest of matter? Like, again, I have my mouse here. If I push this, it's moving at a speed that's not even close to the speed
Yeah,
of light. It's moving
nowhere
at a
near.
speed it's moving at a speed at which normal objects move. And until now, or until Einstein came along, we would have used Newtonian physics to explain the movement and the behavior of such objects. But what Einstein basically did with the theory of general relativity is he gave us a modern definition of gravity, right? Newton's definition of gravity was that any body that has mass automatically emits a force of attraction, and that's called gravity, and it attracts every single object in existence according to two factors, right? Two variables actually, and those are
Mass
the
and distance.
masses and distance, the masses of the bodies that are being
Inverse
attracted
square
and
law.
the distance between them. But Einstein's theory isn't actually based on that. Einstein talks about how massive objects, right, like celestial bodies and the like, they actually warp space-time, right? So you have a massive object like a black hole, right? Something where the force of gravity is just so strong. Light doesn't behave normally near black holes. It actually bends around an object like a black hole. And that's something that Newtonian physics just couldn't explain, right? Because Newtonian physics, things just worked according to a very rigid definition. But Einstein came along and he explained how these massive objects actually warp space and time. Like, again, it's similar to how if you take a trampoline, right, and you drop a ball there. Suppose you drop a ball
A
and it
heavy bowling
spins.
ball.
Yeah, a heavy bowling ball, and it spins around the trampoline, and it spins and spins and spins and goes towards the center. And while it's doing that, it also creates a depression in the middle of the trampoline, right? It lowers the
It
trampoline.
warps the trampoline
Yeah,
surface.
yeah. According to Newtonian physics, the trampoline would just stay flat while all this rolling is happening. But Einstein came along, gave us the modern definition of gravity, and showed how these heavy objects can actually warp space and time. And this
Yeah.
example of the bowling ball is actually what you see in our solar system, right? In the
Yeah.
middle,
So
right, you have the sun. It's a massive object in the middle of the solar system, and because it's so massive, it warps space and time, and it creates a sort of depression where the planets go spinning, spinning, spinning around it, just like the bowling ball would, right? It go spinning around the trampoline while creating the depression in the middle. The sun is so massive that its gravity is that depression, and it causes those planets to go spinning around it, similar to the bowling
yeah,
ball in the trampoline.
I think we've been talking about space time. Actually, I just want to interject and define what space time really is. So basically, special relativity, which we talked about a second ago, connected space and time together in a theory, right? So Einstein took space and time and said space and time is a fabric, like an XY plane. All right, space and time together form a plane, like a trampoline surface, as we talked about,
Yeah.
right? And that is called space time. And these large objects, like Ved said, the sun, black hole, etc., are like the bowling ball in the middle, which warp space time, bend it, right? And that
Yeah.
bending causes gravity. So when space time already warped with the bowling ball in the middle of a trampoline, for example, and you throw another ball at it, or like a golf ball, let's say, right? The golf ball will continue to spin around it, right? Because of depression, the warping of space and time. And Einstein said that is gravity. And that's why planets go around the sun like that, because of that warping of space and time. And that was the general theory of relativity.
Yeah.
Yeah, and just to be clear over here as well, like Newton's laws of gravitation did explain planets moving around. Like they had an estimation of it, but Einstein was just that much better. It was just much more
Yeah,
accurate
it
compared
was
to
so
what
much more
Newton's laws could
precise,
do.
and it could explain it in a very exact and detailed manner, right? Newton's
Yeah.
law still works, right? And they do still work, which is why they still teach it in schools and stuff, right? So like you can explain it for most objects. You can explain the motion of most objects using
With Newton's laws, yeah, it would be
Yeah.
futile to use relativity to explain Ved throwing his mouse, for example. It's just
Yeah,
not
it's not significant
enough
enough, and it's not. And there's
Yeah.
not enough mass to warrant
Or
those
speed.
complex calculations. Yeah, or speed. Yeah. But when you get to stuff that's a lot bigger, like the sun, that's where Einstein's theory of general relativity comes into play.
Yeah, you really got to make sure your calculations are at that stage are
Yeah.
really precise and really accurate.
Yeah.
That's why Einstein comes in. Yeah, that's why he's the most important scientist ever and one of the most important people as well. And that's why we're talking about relativity over here, because relativity actually forms the backbone of space travel, really, right? Like we can't imagine going out in space if we didn't have relativity to help guide us
Yeah.
through it, right? And because of that, we felt it important to talk and really get technical with the physics over here when explaining relativity, because we want to also talk about space travel now in the future in this episode
Yeah.
and a bit over here.
Yeah.
A very interesting side effect, really, or like a very interesting discovery with Einstein's relativity is the fact that you can time travel almost in a way, right? Because of time dilation, essentially, if I was to travel very fast, time would move slowly for me and
Yeah.
faster for Ved. So because of it,
Yeah.
theoretically, if I was to go at like close to light speed somewhere, right, and let's say I go to Mars and come back, right,
Yeah.
I would have aged, let's say, 5 years, for example. Again, it's very hand-wavy math, it's not accurate, maybe not, who knows.
Yeah.
Let's just say, for example, right, I aged 5 years. But because I was traveling at that speed, time was moving slowly for me. And because of that, when I come back, and time is normal for Ved, how it's always been, Ved could have aged 15 years. The entirety of Earth could have moved 15 years into the future, while I only aged 5 years.
Right.
So theoretically,
could-
I have sort of time travel now. I've come 15 years in the future, while I'm only spending 5 years of my own life.
Yeah. So it's actually the difference in time could be a lot more drastic for because again this is
Yeah.
this is hand of the wave way of the hand math actually,
Yeah.
right? Because it's completely theoretical, and no one's actually tried it out because you can't actually go at the speed of light. So
Yeah,
for
no
all
one's
we
actually gone that
know,
fast.
at the speed of light, you could go to some other distant planet or I don't know, galaxy or whatever in like a year and come back, and on Earth everyone will have aged, I don't know, 50,000 years, right?
Yeah, and then
It just
everyone
makes it
knows
so
dead.
much more drastic.
Just
Yeah,
way
exactly. Yeah,
beyond.
humans could be dead at that point. Like you
Yeah,
never
I
know.
think even science, even astronauts who have been in space, like have been in space around the ISS and moon missions, etc., are
Yeah.
actually a small fraction of a second younger than all of us in a way. They've
Right.
like
Yeah.
their time has moved a little bit slowly for them as compared to all of us. Again, relativity is at play over here, but because they haven't really gone that fast or that far beyond Earth, the effects are very minor. But if you were to go into deep space travel and stuff, these effects would become way bigger. I think Interstellar, the movie by Christopher Nolan, is a
Yeah.
great example of it, where they land on a planet, spend half an hour, and go back to the spaceship, while the astronaut they left behind, their friend, ages like 7-10 years.
Right.
And if you haven't watched the movie, I would 100% recommend it. Go watch Interstellar. It's great
Right.
for
It's a great
space
movie.
people who like
Yeah.
are into space. Uh, and yeah, so so far, like we talked about time traveling into the future, you might be wondering, can we go back into the past? So far, there's no way. We don't think we can go back into the past because again, if you were able to go back into the past, that would also violate cause and effect in a way, and you also run into
Yeah,
a
it
bunch
would.
of problems, a bunch of paradoxes, like the grandfather paradox, and it's just really not something that logically seems possible. Forget theoretically or even practically in that sense.
Yeah.
So because of that, if you want to go back in time, you have to wait for a couple of years. Now we don't really know where that's going as of now. But you know what? Let's for 1 second assume that we can travel in space. Let's assume that we can reach light speed. Let's assume that we can, we have this perfect rocket that can take us anywhere in space. We can go at light speed, and we can really go wherever we want to go. Right? Let's assume that happens.
Yeah.
Right? What happens then? Like, what kind of problems could we run into then? Right? Like is it possible then? If I could travel at light speed, and if I could, get the best rocket possible, and I could get the best technology, will I then be able to go to a different galaxy?
Right. I mean, let's look at the situation first, right? Like, how would this work really? If you have this perfect relativistic rocket that's capable of approaching light speed, like how would that start?
Yeah.
You can't directly move at light speed. I'm assuming you'd
You have to
start at
accelerate up
some.
to there.
Yeah, you'd start
Yeah,
at some
I mean, if you were to go from
particular.
0 to light speed in like a second, just the sheer force of accelerating at that speed
Yeah,
and that short amount of
everything will
time
be
would kill you.
obliterated. Yeah, it won't just
Yeah.
kill you, it'll obliterate all the matter involved in
Yeah.
the process.
It'll probably
So,
break everything.
okay,
Yeah,
you know what?
100%.
Let's assume you start at 0 meters per second and you accelerate at a rate of, I don't know, 1 g, right? G is the
Yeah.
acceleration due to
Gravitation.
gravity. Here on Earth, it's approximately 9.8 meters per second.
Let's take it as 10
Suppo-
for this
yeah,
example. Let's take it as 10.
let's take it
You're
as 10.
accelerating at
Suppo-
10 meters per second square continuously, right? From
Continuously,
0. So
like
it's a pretty
forever,
normal
until-
force. You're used to it.
Yeah.
You can comfortably travel.
until you reach the speed of light.
Yeah.
If you accelerate at a rate of 1 g, you would reach the speed of light in a year approximately, right? You
Yeah.
reach
Approximately
light speed in a year. Yeah.
Yeah,
And
it's not
you also
possible.
assume it's not possible, but like just
if
since
you
we're
do,
doing
let's say
the
we do.
theoretical assumption
Yeah.
of the rocket and everything, and then you also have to, in order for this to happen, you also have to be 100% fuel efficient, right? Like the energy, the
because
fuel you're putting
at
in
this
has
point-
to, all of it has to be converted into energy that the rocket is using, kinetic energy.
Yeah,
None of
at
it
this
can be
point,
wasted as
if
like
we're that
friction
advanced
or
in technology,
heat or anything else. Yeah.
our rockets really have to be 100% fuel efficient, like Wade said. Basically, all the fuel in the rocket is converted into energy. 100% of the fuel is converted into 100% of the energy. No heat, no
Yeah.
light, nothing is lost really, right?
Yeah.
And that's the only way that we'll be able to do this experiment, right? Because when you're talking of reaching at speed of light over here, fuel becomes a pretty big deal, because think about it. The more fuel you put on the rocket, the more fuel you need to power that fuel's weight to light speed.
Yeah.
Right? And when you're traveling at millions of light years of distance, that becomes a pretty big deal, right? And there's only so much fuel you can put on a rocket. So to maximize the amount of fuel that's being used, we're gonna assume that we have 100% efficient fuel reaction, which doesn't exist right now. But
Yeah.
theoretically, an antimatter and matter reaction, an annihilation reaction, should be 100% efficient fuel. So let's say we have that reaction in a rocket, right? Completely theoretical. Let's say we have that moving continuously at an acceleration of 1 g, we reach light speed in a year. Even then, we won't be able to travel too far away compared to where we are right now. We won't be able to go really, really far, and that's because of the sheer amount of fuel required.
Yeah.
Alright, let me just put like some numbers out here, right? Let's say you want to go 4.3 light years away. Alright, small distance.
Yeah.
It would take you about 3.6 years in this rocket, and the fuel required would be about 38 kgs. Okay, small amount of fuel, 40 kg fuel, pretty easy to get. You know, you get the fuel, you go.
This is assuming a rocket is 100% fuel efficient.
Yeah, which is not possible right now. So yeah, let's just say it happens. It'll take you 3.6 years. You'll get there with 40 kgs of fuel. Right? Cool. Let's say you want to go a bit further. 27 light years. Alright? It'll take you 6.6 years to get there. And the fuel needed would be 890 kg. No, it's an exponential jump over here. But I think, a ton of fuel's reasonable. We can get that much fuel. We can put on the rocket, right? Rockets are big spaceships. It's doable.
Yeah.
Right? So let's say you go on a nice little holiday, 27 light years away.
Yeah.
But now you're getting a bit ambitious, right? You want to go 30,000 light years away, which is 1/3 of the Milky Way's distance, right? Let's say you want to go across the galaxy to a different solar system, meet some friends over there, right? It'll take you 20 years to get there, firstly. And it'll take you 950,000 tons, not kgs, tons of antimatter and matter fuel at 100% efficiency.
Yeah.
It would take you almost 1 million tons of fuel just to get there.
Yeah. Let's go one step more. Let's go one step further.
Oh, you want to be on that? Okay, fine.
Yeah, let's just see how large the numbers get.
Yeah.
Okay, yeah. So suppose you wanted to go 2 million light years, right? Again,
Okay.
we're dealing in light years, but 2 million is a huge amount, right? 2 million light years.
Light would take 2 million years to cross that.
Yeah, at a
That's how
speed of
many
300 million meters per second.
Yeah.
So 2 million light years, right, would take you 28 years, right, to cover in your rocket. That's
huge.
accelerating.
10 more
at
years than I've lived around here.
Yeah, but it's accelerating at a rate of 1 g. So it would take you 28 years in the rocket, and the fuel needed would be 4,000 million tons. That's 4 billion tons.
Say that again, right? 4,000 million tons.
Yeah. The previously we had 950,000 tons for 30,000 light years. For 2 million light years, 4,000 million tons.
That's huge. That's not. You can't put 4 million tons of fuel in any rocket. It's just not possible.
Yeah, that's not possible. I mean, I don't think you can put 950,000 tons either.
I can't go at the speed of light. Everything is too far away. Even if I was to go at the speed of light, I still can't go too far away.
Right.
It's not looking great for humans, It's I'm not super optimistic.
We're not making it.
Are we ever going to go to space? We're not making it out of the Milky Way. I mean, it's just we're just not there yet. It's just not our cup of tea.
Yeah.
But yeah, you know what? Let's change subject a little bit. Let's talk about something a bit more upbeat, I guess. In a way.
Less
it's
technical.
not really upbeat, is it?
it's not upbeat, but like it's less technical and more like wow, light.
More wow. Much wow.
Much
yeah.
wow. Yeah. So let's talk about
our journey in space. Right?
supernovas.
We've talked about planets. We talked about stars, solar systems, galaxies, clusters, superclusters, observable universes. Right. A very cool phenomenon that happens in the universe. Around then, is something called a supernova. Right. You might have heard the term before. It's a very popular term in pop culture and science fiction. But what does it really mean? Like, what's exactly a supernova, though?
Yeah. So what a supernova basically is, right? It's not simple, but there's a very specific event. It's the explosion of a star, right? Because the way a star works, right? A star has a core that is filled with nuclear fuel, and that nuclear fuel keeps burning, and as it burns, the star shines, right? It gives out light, and that light is a direct conversion of the nuclear fuel into light energy through through a chain of chemical reactions, right? But a supernova occurs when this star explodes, and the way it explodes is all of it happens at the core of the star, at the center, where all this nuclear fuel is located, right? There's usually a change that occurs in the core of the star, and this change leads to a supernova, which is where the star explodes. And we usually can't see these explosions in the Milky Way because there's dust like just clouding the atmosphere in the sky, and it basically obstructs the view, and we aren't able to see supernovas in the Milky Way recently. So Johannes Kepler, right? He was a famous astronomer. Most people will have heard of him. He actually observed the last supernova in the Milky Way, in the early 17th century. It's been
Oh,
4 centuries, and
it's
no
been a long
human
time.
has 4 centuries, and no human has observed a supernova in the Milky Way.
Yeah,
Yeah, and there
that's
are actually two. Yeah, there are actually two ways that this can
no. But
happen.
actually,
Again,
before
I
you talk
said,
about that,
yeah,
supernovas. I mean, although tragic, because it's stars dying.
yeah,
It's the demise of a star, but it's some of the most beautiful stuff ever. I think there are like simulations and theoretical images
yeah,
that we've constructed with computer algorithms about how
yeah.
supernovas really look, and you can check that out online. Actually, it's
I
some of
think
the most beautiful.
NASA's got a telescope called the Chandra Telescope, right? And
Okay.
it discovered the remains of a more recent supernova.
Hmm.
Recent as in compared to the Kepler one. So this one exploded
Okay.
in the Milky Way, I think a little over a century ago, and
Hmm.
NASA's Chandra Telescope actually discovered its remains, and so I think
Oh
they have
wow.
images of that up on their website, or you can find it on Google. And yeah,
Definitely. Yeah.
if you wanna see what a supernova looks like, because it looks really beautiful,
It's
just
one of the
Google
most
it.
beautiful things ever. It's really, really like
Yeah,
a, and the fact that it happens naturally. It's not, we're not making a supernova happen. We possibly couldn't,
yeah,
but the fact that it just happens and it's so pretty,
yeah,
it's really a once in a lifetime thing. I mean, if we get to
yeah,
witness supernova, it'll truly be a highlight
yeah,
of one's lifetime. Because it doesn't really happen very often. We don't get to see
yeah,
most of them happen because they happen too far away. There's too much dust, etc., etc.
yeah.
So yeah, it's really something that's very rare. It's something very cool to see, even though it's a star dying. It's kind of ironic in that sense. But
But
yeah,
now
let's get into
let's
supernovas.
get
Yeah,
back to the physics. Let's get back to the physics
back
of
to the
how
physics.
supernovas happen, right? How they
Hmm.
occur. There are actually two main ways that supernovas can occur, right? Again, it
Hmm.
happens because of a change in the core of the star. But there are actually two main changes that can take place which cause supernova to occur. So the first one doesn't occur in individual stars. It actually happens in a binary star system, right? And
Okay.
as the name suggests, right, binary star systems basically have two stars, right? It's where two stars orbit the same point, right? Kind of just going around in a circle, maybe opposite each other or
Hmm.
closer to each other, but basically they orbit the circumference of the same circle, right? The same point. And in every binary star system where supernova can occur, there'll be one star that scientists and astronomers, astronauts, they nickname it the White Dwarf. Okay, and this
Okay.
White Dwarf star in the binary star system it's a carbon oxygen star. It's comprised entirely of carbon and oxygen, and what it
Hmm.
does is it basically steals matter from the other star. So it's not the other star doesn't explode on its own. The white dwarf, the carbon oxygen star in this binary star system, steals matter from the other star. And what eventually happens is the white dwarf itself, after accumulating too much matter for it to handle, it explodes. It causes a supernova. So it basically has too much
Wow.
matter because it's been stealing too much, and it can't handle that like gigantic amount of matter. There's
Hmm.
something that's supposed it's way more than one star is supposed to have, and
Yeah.
that causes it to explode. And that's actually the first type of supernova that is possible.
Wow. Okay. Yeah, it's a full story to it.
Yeah,
It's a very gradual process that essentially leads to the star in the end dying
yeah,
and exploding during a supernova. Wow. Okay. But that's not the only type of supernova. There are other types. Like Ved said, a star is a core where there's nuclear
yeah,
reactions happening constantly, and those reactions form the remainder of the star. Even our sun is
yeah,
exactly like that. Sun works on basically the same stuff.
yeah,
There's constant nuclear fusion reactions happening in the sun, which raises the temperature, which then has heat. The heat comes out, radiation comes out, and that's the sun essentially. The second type of supernova occurs at the end of a single star's lifetime. So here there's no two stars, there's no moving around in any orbit. It's just one
okay,
star, right? And at the end of the lifetime, as a star runs out of nuclear fuel, basically the helium or the hydrogen that it combines together, that runs out. The core is completely empty now. There's no more reactants to have a nuclear reaction with. And when it runs out of that nuclear fuel, all some of the mass of the star, the entire thing that's built around it, flows into the core. Okay, and basically the core becomes so heavy as the mass flows into it that it can no
yeah.
longer withstand its own gravitational force. So it essentially
Oh,
collapses on itself. It implodes in a way, right?
oh
Which
wow.
sounds very gruesome when you describe it that way,
Yeah.
but that results in a giant explosion, in a beautiful supernova, and that's
So it's
exactly
essentially
what's going
it
to happen to the sun
collapses on
actually
itself. It collapses
in
like into itself.
5.5 billion years. The sun was predicted to run out of a fuel for nuclear reactions in 5.5 billion years, and then a sun will explode in a supernova, and a lot of planets around there are probably going to go into disarray, break, blast, etc., etc. And that's going to be the end of us.
Wow. Speaking of the end of things,
How optimistic. We just keep
Yeah.
going up.
this keeps getting worse, but in a way it keeps getting better because knowledge is power. But no, so
Deep.
yeah, Saksham just mentioned the end of the sun, right? Which obviously
Yep.
is bad because it
Which
means
sounds
the end of
tragic.
the solar system as we know it. But things can get a lot bigger than just the end of the sun, right? So just how big? Well, the end of the universe. All 93 billion light years as we know
Gone.
it. Yeah, all gone.
Yep.
And like
How's
it's
that
something that's actually possible. Like before researching this,
Mm-hmm.
actually, I thought this would be an extremely vague concept, right? I thought it would be similar to
Yeah.
the beginning of the universe, right? No one really knows how it happens. That's
Mm-hmm.
not the case, actually. There are actually three main theories that scientists have come
Yeah.
up with, which are extremely detailed and logical.
Mm-hmm.
And I mean, unfortunately, they also sound very likely.
Very
So-
possible, yeah. The three
Yeah.
theories basically are the big freeze, the big rip, and the big crunch,
Big crunch.
which
yeah.
we at the Fried Circuit have translated into matter stays intact, everything gets ripped apart, and the universe swallows itself. And those are
Yeah,
the three
those
theories
are
that
the
we have of the
casual
universe
terms
ending.
itself. Yeah. So so we start off with the big freeze, which is one of the most probable ones, right? And as Saksham said right now, think of it as matter staying intact. The universe ends, but everything stays intact in a way. And the way this basically works is, everything's expanding, right? The universe is expanding right now, as we know, and has been expanding since the beginning of time, since the Big Bang. So the universe is expanding, will continue to expand, but as of now, the universe isn't uniform, right? There's some parts of
Yeah.
space that are just empty. Some parts have a star, some parts have a solar system, galaxies, black holes. The universe is basically littered with these different attractions and different things. And right now, the universe is completely irregular and non-uniform. But as the expansion of the universe keeps going on, what will happen is this force of expansion the universe is applying to everything will basically smoothen everything out. It'll spread everything that's in the universe, contained in the universe, evenly. The black hole. Suppose you have a black hole on one side with just empty space on the other. The black hole is clearly greater in terms of the force of gravity and mass, all of that.
Yeah.
But as the universe goes on expanding and just expanding over I don't know, hundreds, millions, billions of years, that black hole will just get evenly spread until it's so thin, it's basically like empty space, right? And what's happening here
It's going to
is
evaporate, basically.
yeah, it'll basically kind of evaporate. So that's what will happen with every single bit of matter. Everything will get spread out so thinly, it'll basically be even. The entire universe will be even. The gas
Even
clouds,
to a point
right?
where nothing
and the fuel.
exists, really.
Yeah. The gas
It's just all
clouds
been
that
spread out.
help form stars, right? Those will dissipate. The black holes themselves, as Saksham said, will evaporate. Even the light particles, right? Again, we said they don't have any matter, but they're still there in the universe, still present. The light particles themselves will fizzle out, right? And so everything gets spread so evenly, so thinly, and everything just fizzles out. The universe, in a way, just turns off. It just gets snuffed out.
Just goes out.
So while the matter is still there, still present, it's so evenly spread that the whole universe just snuffs itself out.
It's like putting a
like
fire
candle.
out. It's just gone.
Yeah, exactly. Yeah.
Poof.
Yeah.
Yeah.
And that's quite scary if you think about it. This is everything we know just gone. But
Yeah,
we have two more of those situations for you, so don't worry.
We have two more, and it's up to you to judge which one do you think is the worst. Would you rather be
Yeah.
snuffed out, or would you rather be ripped apart? This one sounds a bit more gruesome, but yeah, the second theory, the big rip, where everything gets ripped
Yeah.
apart. So in this theory, essentially what happens is that when the universe is expanding, everything gets pulled apart. Alright, but because galaxies, like the Milky Way, have mass because of black holes, stars, planets, etc., they stay together. The gravity essentially
Yeah.
pulls galaxies together, but the universe itself is expanding outwards. At some point, the universe's expansion becomes so strong that the gravity that's holding the galaxies together can no longer hold it together. Right? And the small parts like black holes and stars, they get ripped apart. Essentially, everything then gets torn up into small individual particles, and these single particles will just drift around. So basically, how the Big Bang made particles and the matter then combined to form what we have today, these are always going to happen over here. It's going to expand and tear so much that everything's going to come back to the same
Yeah.
particle that started it all, and those particles
Yeah.
just be around, drifting around, and
Yeah,
doing
it's
whatever
so
they
strong
want.
that
Really.
everything will get ripped down to the bare essentials. Every
Yeah,
single piece of
it will
matter, every
essentially
single
tear the
particle.
universe apart. Every
Right.
bit
It'll
of
just
matter is
be
going to get torn
individual
apart.
particles just floating
Yeah.
around. Yeah.
And
And
now
yeah,
we
that's
come to
the
the
second
third
one.
and the final one.
Yeah, the big crunch. Alright.
Okay.
Yeah, and people on the internet seem to disagree, but I personally think this is quite
The best
possibly
one.
the most. I think it's the most terrifying one.
Most
People on the
terrifying
internet,
one.
yeah, people on the
Okay.
internet actually think it's like the least terrifying one. I think it's the most terrifying one because what basically
Okay.
happens here is instead of the universe
Mhm.
sort of shutting down, and like instead of the universe just shutting down and snuffing out
Yeah.
like peacefully like with the candle thing in the big freeze
Big
or maybe
freeze.
in the big
That's
big
my
rip where everything
favorite.
gets.
I think the big freeze is my personal favorite. I'd rather
I think
go
I
out
think
like
it,
that.
yeah, it's the most peaceful one, right?
Yeah.
Yeah, everything just gets snuffed out like a candle, or like in the big rip, everything is ripped apart, but it's still there. It's worse than the big
Yeah.
freeze, in my opinion, but like still there. The big crunch, according to me, is the most horrifying one and the most
Destructive.
sci-fi one, which is basically
Yeah.
the universe swallows itself. It just consumes itself, and then it's just gone out. So I'll tell you how this happens.
Okay.
How scientists think this will happen. So it basically happens here is gravity slowly but surely becomes the most powerful force in the universe, right? Because the gravity of the universe, at its core, that's holding the universe together, it will slowly become the most powerful force in the universe. And because of this, because the force of gravity will then be greater than the force of expansion, the rate of expansion of the universe will decrease. And as this
Okay.
goes on, as the gravity becomes stronger and stronger and the force of expansion becomes weaker, the universe will not only stop expanding, it'll actually start shrinking. And when the universe
Oh.
starts shrinking,
So it's the
things in
opposite
the
of the big rip, essentially, where gravity becomes
Yeah.
more powerful than the
Right,
expansion force.
right. Yeah. And what happens here is not like it's not things won't get destroyed because you can't destroy matter and energy. Everyone knows that. Things won't destroy. Things will just get compressed and get compact and just closer to one another, right? So
Yeah.
these galaxies that you have, they're extremely spread out and far away from each other. These galaxies will, because the universe as a whole is decreasing in size, the galaxies will also get forced together until they actually meet. Then entire galaxies will crash into each other, right? And when stuff like this happens, when you have
That's a big
so
crash.
much, yeah, when you have such large pieces of matter crashing into each other, the temperatures will go straight up, right? There'll be forms of heat that have never been seen before, and these levels of heat will actually rip atoms apart and they'll cook stars from the inside. It'll be such large scale destruction that entire galaxies will get ripped down to their atoms. And stars themselves, stars that burn so brightly and are so hot,
So hot.
they get cooked from the inside, right? And this has happened. This has happened to the
Imagine
smaller.
cooking a nuclear fusion reaction. Like
Yeah.
a nuclear fusion reaction is the most powerful reaction that we know on Earth, at least the biggest way to
Right.
generate energy, essentially.
Right, right.
Imagine cooking that.
Yeah, exactly. And yeah, basically, it'll start off with the galaxies, right? Galaxies crash into each other, and obviously, the smaller pieces of matter, like the planets and black holes and all, will also crash into each other and get destroyed, get ripped apart. But that's where black holes are special because black holes consume matter, right? Black holes
Okay.
have this huge force of gravity that consume matter. And when black holes crash into each other, they won't get destroyed. Black holes will just crash into each other and converge into bigger black holes. And as this happens with more and more black holes, as they individually consume other matter and combine to form bigger black holes, it'll all eventually, just before the big crunch happens, it'll all eventually converge into this one mega black hole that ends up swallowing the universe. And that's
okay.
how the
What's going to stop
that's how the
existing?
big crunch
It's gonna
happens.
all roll up in a
Yeah.
ball, go inside a black hole, never to be seen again.
Yeah, I think that's the most terrifying one.
Yeah, I think I'll back you on that. Oh god, that does not sound good. But you know what? On a slightly happier note, right? All this is gonna happen billions of years from now, when we're all gonna be dead, and humanity probably won't exist anymore. So we should be fine for the most part.
Right.
We hope. Anyway, you
Yeah.
know, despite all this, even if
As far as
somehow,
humans go, we'll be fine.
yeah, even after all this, assuming you were still somehow brave enough to venture out into the depths of space, we're now going to talk about space exploration, right? Who wants to go to space? Personally, I'd love to go to space. Like if I got to go to the moon, to Mars, short distance trips.
They seem like small
take
ambitions
those.
now compared to everything we've discussed. But yeah, short distances.
Definitely,
Yeah.
I'd love to go to space, and I'm not the only one. There are actually a bunch of billionaires, almost like a race between the billionaires, who want to go to space and who want to start commercial space travel. Richard Branson
Make
was
space
Galactic.
tourism an industry.
Space tourism in industry, yeah. It's they're creating
Yeah.
essentially what's a new industry and supplying everything for their industry themselves,
Yeah.
right? And I find it quite cool actually. Like if I could get to buy a ticket to a plane that'll take me to space for like a day or two, and then I can come back.
Yeah.
That sounds pretty cool to me. I mean, I'd definitely do it if I could afford it.
Right.
But yeah, so
It's
Richard
going to be
Branson-
incredibly expensive.
Oh yeah,
Yeah,
I think
we'll cover that
tickets
right
right
now.
now are $250,000.
Yeah, they're
somewhere from there to, like-
$250,000. Oh, these are the
Yeah.
Virgin Galactic tickets. Richard Branson.
The
We're
Virgin
going to talk about
Galactic
right now. They cost around $250,000 each, and so far they've actually generated revenue north of $80 million.
Wow. Okay, people
Yeah.
really want to go to space.
Yeah,
But-
which means more than what 32 tickets have been bought.
Yeah.
320, 320, my bad.
320 tickets have been bought. Yeah.
Yeah, my bad.
That's incredible. But yeah, so Richard
Yeah.
Branson, owner of the Virgin Group, owner of Virgin Galactic, on July 11th was the first person to make a commercial space flight.
Yeah,
Right.
That was just 5 days.
He's
ago.
beat everyone, and his company Virgin Galactic is now offering people commercial space flights. But there are some questions regarding its validity because he only went up 86 kilometers in space, which some are saying isn't the official boundary of space, even though the US considers it to be. Some people say you have to go at least 100 kilometers up there to
Some
actually
people are
call
saying
it
he
space.
just made it to the extremes of our atmosphere. Not actually
Yeah, he didn't really
into space itself.
go what's called space.
Yeah.
But who knows? So far, he is the first billionaire to make it to space. Someone who's hot on his tail, Jeff Bezos, with his Blue Origin company. He's actually
Right.
flying on July 20th, which is 4 days from now. He's going to take to the skies and go to space. And
Very close.
we
The
see
billionaire
how
space race.
the billionaire space race. How is this even a term? How is this a real thing?
Yeah. Like no one would have believed you maybe like a year or two ago if you actually
Yeah,
talked
that there will be
about
billionaires
the
racing to
space
go to space.
race. Yeah.
But yeah,
But now
even
it's
his
happening
company,
in the same fortnight.
in the same fortnight, yeah, exactly. Even his company, Blue Origin, wants to offer commercial space flights where you can pay a bunch of money, get on a plane, go to space. I'm down, honestly. If I could, I would definitely do it.
Yeah.
But you know
it's
what?
expensive and hasn't been tested yet. But eventually, who knows, right? Might become
who
more
knows?
affordable. It'll be tried
Who
and tested
knows?
for sure. People will be dying to go out in space.
Oh,
Maybe
100%.
literally.
100%. It's definitely a very big attraction for people. But now we come
Yeah.
to our favorite billionaire, a man who we've mentioned now on 3 episodes out of 4 of the Fried Circuit, the Doge father himself, Elon Musk, with SpaceX. How can we ever cover a topic without talking about Elon Musk? This
He's
man's
doing
got his
everything.
hands everywhere. He's doing everything.
Fingers in every pie. He's just
Yep.
working in every industry.
Changing the world.
Wow.
Elon Musk.
Yeah.
We love you, Elon Musk. Please come on the podcast, please. But yeah, essentially his company is called SpaceX. They have a slightly different model. So far SpaceX I think is the longest running company, I think, out of Blue
Yeah.
Origin and Virgin Galactic. They've been around for a long time. They're doing a lot of cool stuff. They're more focused on making rockets that can be reused after flight. So basically, before, when we used to have rockets going to space, they used to come back on re-entry and burn up, essentially, and get destroyed on the way back, right? SpaceX has successfully made rockets that could go up to space and come back and land, and then can be reused again to go back to space and come back. Now, this significantly reduces the cost of space travel, which makes it much easier in the end for us to go to space in a more long-term sense, right? So,
Yeah.
and SpaceX's ultimate aim, as stated on the website also, is that they want to colonize Mars and also put a network of satellites up around Earth, right?
Yeah, the Starlink
and the Starlink satellites, exactly. And creating reusable rockets is the first step to that. Like, we can't colonize Mars and have direct flights to there unless we can use rockets again and again. Otherwise, the cost is prohibitively high.
The cost is way too high, which is why Elon Musk and SpaceX and actually a few other companies, but primarily SpaceX, are experimenting with reusable rocket stages, right? The stages of the rocket are basically the parts that get disposed as the rocket takes off, takes flight. So that actually, so it has a first stage, a second stage, a third stage. And those get
Yeah.
disposed of as the rocket goes further into space. So SpaceX, and because of them, a lot of other companies are actually experimenting with reusable rocket stations. I think they have been successful with this, which is a huge. It's a huge
Yeah.
step in the right direction, because this is essential. You can it's like if you
Mm-hmm.
have a car and you replace the car every time you make a trip, right? You buy a new one. That's
Yeah.
just that just won't
Wasteful.
work. Yeah.
This is not doable. Yeah.
That doesn't work in the long run. The same way, you need to be
Mm-hmm.
able to reuse these spacecraft, and I think what they're doing is they're making it go in the right direction. And he's actually been kind of a pioneer in the private space flight industry,
Yeah.
because for a long time spaceflight was dominated by the national organizations, especially NASA.
Yeah.
But
It's only been like a
spa-
government thing before. SpaceX was the
yeah,
first private organization to really make it
yeah,
big in the
private
in the space
organizations
way.
couldn't compete.
Yeah.
But now, SpaceX actually became the first private corporation to
Yeah.
send supplies up to the ISS, the International Space Station.
And astronauts up to the ISS actually.
Astronauts
They recently
too, yeah.
sent American astronauts up to the ISS.
Right,
Yeah.
yeah. And
Which, for those who don't know,
SpaceX
is the
does,
International Space Station. It's a big science lab that circles around the Earth in space
right,
and
yeah,
allows to do cool
and
stuff in space. Yeah.
yeah, and collaboration between different countries. But yeah, SpaceX is one of the biggest companies to have like major contract with NASA, and that's why since NASA has like recently lost the ability to send astronauts to space, they rely mainly on SpaceX now.
Yeah.
And
SpaceX is the
SpaceX is
only
actually
US
integral.
company
Yeah,
or organization that sends people
yeah,
to space right now. NASA doesn't send people to space anymore. It's just not a thing they do.
right, right. Yeah,
Yeah.
and they rely on SpaceX spacecraft.
Yeah, and
the next stage is just commercial spaceflight.
oh yeah, obviously. I mean, like all other billionaires, even SpaceX
Right.
wants to send people to space. Commercial spaceflight is the new thing, and it's gonna be very cool. I can't wait to see like in 5 or 10 years if we can actually go to the moon, like for a holiday.
Right.
It seems like a pretty cool thing. But speaking of going to the moon, I mean, if we want to get serious about going further into space and going to Mars, etc., we can't
Right.
really rely on launching from Earth. And because of that, most people say that we need to actually have space bases, right? More than the ISS.
Yeah.
Like ISS is just one of them. People say that
Yeah.
we should actually establish bases on Moon, where we can then launch further missions from the Moon, which would significantly make it easier for us to go to space. I think that's the next frontier. Like in the next 5-10
Right.
years, we're going to see NASA, who's already announced actually, by the way, in Project Artemis that they're going to be sending astronauts to the moon. But not
Yeah.
only NASA, like other organizations also, we're going to see them sending people to the moon again after an incredibly long time, and creating like space bases and space airports and launch pads on the moon from where we can then go to Mars and other areas. And a very cool
Yeah.
innovation that I saw about in the papers the other day was actually using lunar rocks and lunar dust to 3D print like objects over there.
Right,
Essentially, you
right.
could like create
So,
things on the moon by using
yeah.
resources from the moon itself, without having
Yeah,
to send
so-
stuff from Earth to the moon, which is very cool.
Yeah.
And,
So this
uh,
reduces like the cost and the need for fuel, obviously, because you're taking less load from Earth. But also you find more resources there, right? Because you, as well as Earth's resources, you have the moon's resources to utilize. And this again, it's similar to the moon base project. It just helps optimize the whole project. Make it less cumbersome to go entirely from Earth to space or other planets. The whole
Yeah.
trip, you can just go like a few
it makes
hundred
us a
kilometers
properly
closer.
spacefaring species now. Like
Yeah,
humanity,
it does.
it owns
Right.
space now.
Yeah,
Yeah, but I think that's like the next frontier. Like from commercial spaceflight, we're gonna go to like moon bases and
Yeah.
taking off from the moon.
right.
And yeah, that's about it. I mean, that's the end of the episode. That's all
Yeah.
we're prepared for. Some of you might have noticed that this is a different format of recording, really, because we ran into internet problems and a whole bunch of logistical
Yeah.
problems. That's why we're actually recording in a very different way. So let's
Yeah.
see. if
But
it's a
hopefully the
proper
quality will
edit.
be the same.
Yeah, hopefully the quality is the same. the
Ideally,
audio
you'll be able to
works.
tell.
I didn't want me to tell, but yeah, in case someone was
Yeah.
wondering, yes, we are recording in like a different setup altogether, and we've had to change
Yeah.
significantly
Right.
to make this possible.
Yeah.
But yeah, that's
I
pretty
think
cool.
we
That's
ended on
space.
we ended on a pretty optimistic note after all the
Yeah.
death and destruction before that.
All the death and destruction and all the stuff that we can't do.
Yeah.
We'll actually end on a very positive note, where stuff that we can do and stuff we're looking to do and we're going to probably see in the next near future. I'm very excited. Personally, I love
So
this
am I.
space. Like,
So am I.
sector,
I've been
space.
following
Uh,
like space and especially private space flight. Actually, no, private as well as governmental space flight. I'm following it for a while now. And it's every
Yeah.
every few days there's always like an interesting development. Right now, we'll
100%.
be looking at Jeff Bezos' flight in 4 days.
On March,
5
on
days.
July 20th, sorry, not March.
Yeah.
July 20th,
Right.
and we're gonna be watching
4
it live.
days.
Yeah.
Yeah.
I mean, you guys should watch it. Whoever's watching,
Yeah,
if
everyone-
this goes out
everyone
before
watches-
20th,
Yeah. Just watch the broadcast.
watch the space flight. Tell us how you saw. Tell us how you liked it in the comments.
Yeah.
Tell us if you go to space in the comments. You know, would you want to go to space? We don't want to go to
Yeah.
space. Is it too scary? Yeah, let us know. Like, share,
Yeah, let us
subscribe.
know. And we'll
And
see you
we'll
next
see you
time.
guys next time. Yep.
Yeah, just keep
Peace.
watching.
See you guys. Keep
Bye.
watching.
Bye.
Yep.